Right, so today, the topic is, if you guys still remember, last week, we talked about the principles of energy and thermodynamics, yeah, but we've stopped before we entered heat. So in this video, okay, we will look into heat and temperature, okay, and basically the thermodynamics of energy, right? So learning outcomes, I know you've seen this last week, but basically today we are going to look at the second and the third learning outcomes. First is to know the definition of heat, yeah, and then we can understand the law of thermodynamics in the context of energy. So that's what you're going to be learning for today. There will be, I guess, 2 videos for this one. And I hope you guys will be able to learn and, eventually understand what this is all about. Okay, so first things first, what is heat and temperature? Is it the same thing? Is it different? Of course, you don't say like the spelling is different, okay? So it's actually looking at different things, right? So with temperature, it's actually the measure of the average kinetic energy of individual molecules, okay? And whereas for heat, it's actually the energy itself, okay? The energy that is transferred from one object to another because of the difference in temperature. And if we talk about the internal energy, the sum total of all the energy of all molecules in an object is called the thermal energy. Okay, so if you look at the figure down here, okay, what it actually is yeah? When we talk about temperature is the measurement. Okay, and when we say measurement, it means must have something that you measure something with. Okay, it must have an equipment or a sensor, measuring something. Okay, and in this situation, temperature is actually, it actually measures, that everything, okay, like I mentioned last week as well, okay, everything, the atom, okay, it has its own kinetic energy. It is vibrating, okay, at its own frequency. And we can say that everything has, an average kinetic energy. Okay, it's no matter how cold it is, it's gonna have at least a minimal point of kinetic energy. That's why if you've ever wondered, okay, about that temperature, it can be measured in degrees Celsius. That's what we usually use, okay, and also Kelvin. Okay, and usually for Celsius, we have 0 degrees Celsius, right? For, quite cold, but it does goes beyond that. It goes into the negatives. However, if you notice with Kelvin, there is no negative. Kelvin is actually the infinite point. It has no negative 1 Kelvin, for example. Okay, and this is the point which relates to that, because it is not possible for something to be at 0 Kelvin, because this would mean that something, okay, the atom, it doesn't move at all. Okay, it doesn't vibrate. We're talking about this at the atomic level, okay, like this one, at the atoms. Okay, it doesn't vibrate at all, then it will be 0 Kelvin, but it's not possible. You can't find it in nature, okay? So if you look at that, that is temperature, okay? So even though when we use the thermometer like this, okay, and we get the readings, it's actually measuring that vibration. It's measuring the energy of that, okay? That what that is what makes it different from heat. If we're talking about heat, heat is the energy. Okay, and it is transferred, of course, from things that are hot to things that are cold. Okay, and we'll look at a couple of examples later on, right? And so I'm just stressing this here, okay, so you can understand, yeah, and you can look, yeah, anytime, every time you go into, so nowadays it's endemic phase, you don't really do the temperature checks anymore, but every time you see the thermometer, okay, you will actually understand, okay, it's not measuring, there's nothing called temperature in your body. Okay, it's actually a measurement of something, okay, the heat in you, right? Okay, let's move on. Okay, so just very quickly on this picture though, if it's cold, the vibration is not that high. That's why I mentioned just now, even at the very coldest, it will vibrate. Okay. But if something is hot, if the same thing, you heat it up, okay, it's going to vibrate more. Okay, and of course, that vibration, that movement, okay, it correlates to kinetic energy, right? And all of this energy, okay, it is, if you sum it all up, okay, the total of those will be the internal energy. Okay, and we call that the thermal energy because that creates heat within the molecules. All right, so heat propagation, okay, how does it move? Okay, you know that, just very quickly, if we look at the figure below here, right? Okay, if you cook something, I'm sure at least, once in your life, we have done this. Masak Maggi ke, masak air ke. If you're cooking something, and you heat something up, basically, right? So what happens is, there's always going to be, okay, not always the case, but in heat propagation, we talk about 3 methods, okay? And it's always going to be from a heat source, okay, where it is having a higher temperature, to a heat sink, okay? And sink means it's lower temperature. And there were always going to be 3 elements: conduction, convection, and radiation. Okay? Of course, these are things that you have learned before, yeah, and I hope you guys still remember. But what it is, if we're talking about conduction, we know that just now, heat, it comes from the vibration of the particles. You know, something is hotter than something else, then it's going to move. The energy is going to move from when it's hotter to another place where it's colder. Okay, so what happens is that the vibration just now, okay, remember when I say that the particle is heated, it vibrates much more vigorously. Okay, that state of vibration, okay, it communicates the motion to the neighboring particles. So imagine if you have this here, like these ones are full of atoms. Just imagine that there's 1 layer of atoms there. Okay, that is in direct contact with the heat source, okay, the fire. Okay, so the atoms here will vibrate more, okay, and the heat will move from here to the ones next to it. Okay, and that's what the transfer of that motion is what we mean by heat propagation through conduction. It's from contact, okay, of the particles. If we're talking about convection, okay, convection here is hot liquids and gases are less dense than cold ones. Okay, this is related to physics as well, if you guys still remember. Therefore, hot gases and liquids rise and are replaced by cold ones, which become heated. Okay, so what happened is, okay, through the pan, that's what happens, the conduction, but the water inside, the liquid, okay, the ones below, okay, just now we talk about convection through the pan material, but it also happens to the liquid. Okay? So as the liquid becomes hotter underneath, it's going to move up, okay, because it's less dense. Okay, and whenever things go up, the remains will go down. And it goes here, it receives energy again, it goes up again. So, you know, that kind of motion, it creates the heat propagation, it creates the heat transfer. Okay, that is through convection. And lastly is radiation, and this involves electromagnetic waves. And this is mostly through, you know, when you're sitting, if this is a barbecue, okay, and you're sitting there, okay, that's the stick man, okay, you're sitting there, someone else is holding the pan for you, but you're sitting there, and you still feel the heat, okay, and that heat is through radiation, and it's through the electromagnetic waves, okay, that is transported from the fire to you. Okay, so those three, okay, this kind of situation, it perfectly sums up what is happening with the three different methods of heat propagation. Okay, right. Now, we know about temperature, okay, we know about heat. Now we look at what exactly is specific heat. Okay, so specific heat is actually, okay, the amount of heat required to change the temperature of a given material with mass m. Okay, try and look at that and let it sink. Okay, what is actually this sentence is talking about? Okay, so let that sink in first. We'll look at the example. Okay, specific heat, right? Why does something, some materials heat up faster than something else? Okay, and that relates to the specific heat. And again, using the cooking analogy, okay, there are different types of materials used to make pans. Okay, I'm not sure if you know or if you notice, okay, but there's actually different materials. Some use aluminium, there's some that use copper, you have stainless steel. Okay, there's so many different materials. And actually, those different materials, if you're really like a cook, you would notice some types of pans are suitable for some kind of dish. Yeah, but usually we just use everything with the same pan anyway. But it relates to this lah. Basically, if you have something that is easily heated up, okay, whatever that you're cooking is going to be burned really, really quickly. Okay, because the transfer of energy is so fast, right? And that relates to this, the Q. So this is the specific specific heat, and of course, this is at different units. Okay, so we'll just look at one. Let's look at this one. This is the SI unit. Okay, and basically what it's saying is that for if you have aluminium, okay, aluminium requires 900 joule. Okay, and this is the amount of heat required to change the temperature of a given material with mass m. So if you have the same pan, one is aluminium, another one is, let's say, copper. Okay, and take note of the numbers there. So in aluminium pans, you would require a lot more heat to change the temperature of the pan. And with copper, you would require, I mean, even less than half of that. Okay, and what that means is that copper pan is going to heat up much, much faster compared to aluminium. But it's exactly what that means. Yeah? If you have the similar mass lah, okay, so let's imagine both pens are 1 kg, okay, and you heat it up side by side, copper will heat up much faster, right, compared to aluminium. And that's the analogy that you can look at. All right, now bear that in mind. Okay, always try to remember that Q equals to MC delta T. Okay, because it's going to help you a lot. Hint for quiz, eh? Right. Now we look at calorie. If you notice here, we have cal. So cal here is calorie. Okay. And what is calorie? Calorie is actually a common unit for heat. Here we have. So what it is defined as the amount of heat necessary to raise the temperature of 1 gram of water by 1 degree Celsius. Okay, and it follows if you have 1 kilocalorie, okay, we denote that as kcal. It is the amount of heat necessary to raise the temperature of 1 kilogram of water by 1 degree Celsius. Okay. And sometimes you may also find BTU. Okay, BTU is another unit that is also related to this. Okay, and it means that the amount of heat necessary to raise the temperature of 1 pound of water by 1 degree Fahrenheit. So that is if you're using a different unit. Okay, this is US unit, Fahrenheit and LB, just pound lah. Okay, so basically, this is also related to your daily life juga lah, calories. People say that if you want to lose weight, you have to count your calorie. Okay, this is exactly what it means actually. And if you look at any nutrition facts, yeah, like this one, this is Coke. Usually they'll put in this one, okay, to indicate how much, because people are counting calories. So it will say, okay, in 1 bottle, 200 calories. Okay, and that will, you can either translate that as you will need 200 lah. Okay, amount of heat is 200 to raise temperature of 1 gram of water by 1 degree Celsius. Sorry about that. Okay. And if you have something higher, okay, and that will immediately relate to the amount of heat, the higher amount of heat. Okay, so why do people count their calories? If you have more calories in 1 day, okay, you're gonna need a lot of heat to burn it off, so to speak lah. If you are on diet, okay, you want to lose weight, okay, we need that heat. And where does that heat comes from? That's how your own metabolism, your body, it requires certain amount of energy to keep going. Okay? But that's also when people do exercise. When they do exercise, they have the higher amount of physical activity, and that will increase the energy requirement of your body. Instead of you sleeping, compare that to you running. Okay, of course, these two activities will require different amounts of energy. Okay, so if you're running, the higher amount of energy required means that your body have to work extra time. It has to use all the calories. Okay, if you eat something, it will burn that. And your fats, okay, fat is your body's way to store energy. Okay, so so this is more towards food nutrition. I'm not going to go too deep into that, but what exactly is that at one point, your body will need to use your fat, okay, to give you energy, right? And that's how people try to reduce their body weight. okay, through exercise and also through nutrition. So you count calorie or you do diet, so on and so forth. Okay. So putting things into perspective, okay, this is just something to share. Okay. So if previously, I think this one is no longer there. I checked previously, it's no longer there anymore. But previously in the UK, okay, the Coca-Cola, Coke, they actually have a work it out calculator. So it's basically saying that you choose whatever products, Coke products, and it will tell you what are the activities that you can do to burn off that bottle of Coke. Okay, and to put it in perspective, if you do things like this, yoga, 226 kilocalorie per hour. Okay, that is if you do power yoga for 1 hour, then you can burn 226 kilocalorie. Okay, and you have to look at this one as well. Okay, water, even water, it has the Coke here, 139 calories. Okay, and you need to work out for around 22 minutes of aerobics to burn that off. So I'm not saying don't eat, no, but if you are talking about, making healthy nutrition, healthy life choices, okay, it all works together lah. You can always, I usually just proceed with eating whatever I want, okay, but you have to control your portion, right? And of course, at the same time, adopt a healthy lifestyle, okay? Now, calorie, okay, this is also something that you have to remember, guys. The mechanical equivalent of heat, 4.18 joule is 1 calorie. Okay, remember just now what is calorie and what is actually joule. Okay, and if you have kilojoule, then it so follows that it's going to be kilocalorie. Okay, the same. But if you have 1 BTU, it's going to be 252 calorie, and that is equal to 1055 joule. Okay, so very quickly on this lah. Yeah, and now just again sharing with you the amount of energy in food. Yeah, I know that now it's Ramadan, people are fasting. Okay, those of you who are Muslim, you are fasting. Okay, and actually, if you have nasi lemak, one portion of nasi lemak, the energy is 1635.90. Okay, and that actually means that you have to work out to burn that off. Yeah. And this is also, it follows from what I mentioned before, okay, about the counting calories, so on and so forth. Yeah. So it actually, in terms of energy, you can imagine that your body is a system, okay, and you are doing something. The more the energy requirement is needed, the more input that you would need. Okay, so imagine that is your body. Okay, I'm going to use stick man again. Okay, your whole body, things that you eat, those are the things that is the input to the system. Okay, and within the system, you're going to produce energy. Okay, and that energy is used basically for all of your physical needs lah. You're walking, you're going somewhere. And even while sleeping, you're burning calories because there's some functions that never stops in your body. Right? So imagine that and compare that again to power plants. Okay, I'm just going to use that. Okay, the same thing. Okay? You can look up the energy in coal. Yeah, in coal, okay, it's the same thing. If you're looking at this as food for us, okay, we can actually say that the food for the power plant is coal. Okay, and you can actually know how much is the energy, okay, and how much of energy is contained within that coal, okay, per gram, for example, and you can actually calculate how much electricity can be produced. Just like we can calculate our energy requirement in our body. All right, so I'm not going to go into this. You guys can always look it up if you're interested. Okay, but this is again another correlation that I would like to make a point of. Okay, when we're talking about energy, it's all around you. It's all around you. You turn on your computer, requires energy. But even in your body, okay, also requires energy. So a human body uses energy in many ways. The metabolism is fine-tuned to ensure all functions of the body is maintained. So we're talking about a system now. Okay, and remember just now, I was talking about your body needing to burn the fat. Okay, so actually this is related to oxidation of fat. So oxidation, the easiest way to remember it is always oxidation. It's something where you break it. You break some bonds, for example. Okay, so imagine the fat inside your body. Okay, and now you're doing something lah. Okay, you're doing. If you look at the figure on your left, okay, basically you can actually measure, okay, how much power is generated by each activity that your body do. Okay, if here it shows like blood pressure, arm motion, you know, footfalls, finger motion, those are the things. If people ask, how did you measure this? How do you know how much energy required to do this, for example? Okay, you can actually calculate that. And one simple example, or rather, I'll just give a high level example, okay? So if you have fat in your body and you're working out and you're wondering how much fat you're going to reduce through certain activities, okay? So maybe for how long, so on and so forth. So if we're talking about, this one is fat, basically 10 kg of fat. This is a chemical process, yeah, oxidation of fat it's called, okay, this process. So you can actually calculate lah, basically. 1 kilo of fat requires, 1 mole of fat, okay, requires 78 moles of oxygen, okay, and you will breathe out 55 moles of CO2 plus 52 moles of H2O. So this is in mole. But to make it more, so you can imagine something much closer, this is in kg. Okay, so 10 kg of oxygen, of fat in your body, okay, you can do that. You can actually, you will actually produce 8.4 kg of CO2, okay, plus 1.6 kg of water. Okay. So you can actually calculate the heat, the specific heat for this, okay, and what are the energy requirements, okay, that enables this 10 kg to be used up. Okay, so you can correlate that actually, okay. And also this process, apart from being called oxidation of fat, we can also call it as combustion. Okay, and combustion is a term that we use a lot, okay, especially if we're talking about energy and if we're looking at what's happening in power plants. Okay. So we move on, okay, to this now. This is about calorimetry, okay? And calorimetry is actually looking at how the energy changes in a system. Okay, so for example, if you have an open system like this one, the mass and energy may enter or leave the system. So this is a theory, okay? This is the basic theory lah. Okay, I'm just going to share with you because usually I refer to these terms a lot, like open system, closed system, isolated systems. So I hope you can understand what is the difference between the three. Yeah. So if we're talking about open system, then it means that both mass and energy may enter or leave the system because it's an open system. Whereas if you have a closed system, no mass may enter or leave the system, but the energy may enter or leave the system. Okay, so imagine this one lah. So this one is not closed, kan? Tak ada tutup. So you can actually pour in something. Okay, and energy inside here, it may go out. Okay, it goes out by radiation, by conduction, by convection, right? In closed system, you close it, okay, and the mass, okay, the thing inside is still the same. Okay, nothing can go in or go out. However, energy can still enter or leave. If you have fire there, okay, it's still going to heat up your system here. Okay, but the third one, if you have an isolated system, okay, even first, of course, the mass cannot enter or leave. Okay, but energy, if it's an isolated system, no energy may enter or leave the system. Okay, because it's isolated. Okay, that is insulated because it's insulated, yeah, and it's isolated lah. Right. So knowing that, okay, and try to think about this one. So calorimetry is a quantitative measurement of heat exchange. Okay, this is the definition. Right? And a calorimeter is a device to make calorimetry measurement. Okay, so calorimetry tadi is the measurement, the quantitative measurement, and this is actually the equipment lah, the device. Okay, and this is an example of a calorimeter. Okay, and what it does actually is it is an isolated system. Okay, isolated meaning that the mass is conserved, it's there, and energy is as well. Okay, so what happens is that any energy or any heat released by the combustion chamber will increase the temperature of the water in a measurable way. So this is actually, we want to measure lah, the changes of the temperature, and this relates actually to the specific heat of something. Okay, so imagine you have a sample, you don't know what is the specific heat. So how are you going to calculate that? How are you going to know what is the specific heat of this particular thing? Okay, and using calorimeter is a way to do that. So you put in your sample here, okay, and this is actually a combustion chamber. Combustion, always remember, combustion means it's being burned, dibakar, it's combust. So of course, okay, thinking about fire, what do you need? You need the material, kan, to be burned. So what happens is that the heat released by the combustion chamber, and the combustion actually happens as the thing here is being burned. Okay, that heat will increase the temperature. Remember the conduction just now? Okay, and because it's an isolated system, okay, the temperature will move outwards. So imagine this is the, that is the combustion chamber. Okay, the heat will be moving, okay, throughout, okay, at all generation, at all direction. Okay, but it will stop here because then it's insulated. Okay, so it doesn't go through. And you can definitely now, you can measure, okay, the difference. So before the combustion start, you will measure the temperature. And after the combustion finish, okay, you will know what is the change in temperature. All right. And why is this significant? If you remember a few slides back, we talked about specific heat and also the equation. If you know the mass, okay, you know the mass here, the sample just now, okay, and you know the difference in temperature, then you will be able to calculate the specific heat, right? So this is the equation just now, Q equals to MC delta T, okay? And you can use this interchangeably, right? So just now it was water calorimeter because you actually measure the changes in water temperature, okay? But there's also this one, it's called bomb calorimeter, okay? Generally doing the same thing, yeah? Generally doing the same thing. So the only difference is within the combustion chamber, okay, how the combustion is done, right? Now, calorific value. Calorific value is defined as the amount of calories generated when a unit amount of substance is completely oxidized and is determined using the bomb calorimeter. Okay, and this is what I mentioned just now as well. So you know an amount of substance, okay, you know the mass, and that is burned at constant pressure and standard conditions, okay? And the heat release is captured in a known mass of water, okay? Remember just now we checked the temperature before and after combustion, so you know exactly how much heat is released. Okay, so if the initial and final temperatures of the water is measured, the energy release can be calculated using this equation. Okay, this is basically what we're talking about just now, the calorific value as well. Yeah, and you will be able to basically measure the calorific value of anything, okay, using this way. Right? So these are some of the well-known substances that you use as fuels. Okay. Hydrogen, methane, gasoline, diesel, coal, firewood, briquettes. Okay, and you can actually see how much is the calorific value, and this is determined using the method that we've looked into previously. Okay, and actually we come to the end of the lecture. Okay, so I hope you guys can understand now what is heat and what is temperature. Okay, what is calorie, okay, what is calorific value, what is specific heat. There's a lot of terms that was used before. Okay, so make sure you are able to differentiate between all of those. Okay, and for example, you will know how to calculate the calorific value of some materials. Okay, and I'll see you in the next video. Right. Bye.